Hi everyone, I'm Professor Burgasser, and in this video we're going to be talking about the transformation between our main kinematic quantities, position, displacement, velocity, and acceleration. In this video we're going to be talking about the average quantities of velocity and acceleration. In the next video we're going to be talking about how we do those through instantaneous measures. This will be based mostly on algebra. The instantaneous is based mostly on calculus. Now before we begin, it's important to make sure we review our definitions of these kinematic quantities. Right? The position is the location of a point or an event relative to the origin of your coordinate system. So if I have a rectangular two-dimensional coordinate system here with x and y, I can specify different points, and the position of those points on this coordinate system is specified by a vector that goes from the origin to that point. And I can specify these for any of the points on my diagram. The displacement is the difference between two positions of points on any coordinate system. And importantly, the displacement is actually independent of the coordinate system because it's just a vector that points between two different events. And so if I take my points A and C here, the displacement, which goes from A to C, delta R AC, is just defined as the position of point C minus the position of point A. And it turns out that that quantity is actually independent of the coordinate system itself. Our next quantities are both rates. The velocity is the displacement over time, and of course it measures how fast something is moving. And so if there are two time steps between A and C, I can calculate that velocity. All right, it's the displacement over that time step. And the acceleration is the change in velocity over time, so it's a velocity rate. And that's going to tell us, it's going to be intimately linked to the forces acting on an object. So to start looking at how we transform between these quantities, we're going to look at the averages, the average displacement, average velocity, and average acceleration. And for this part, we're going to be looking at a particular sort of numerical example. I've got my coordinate system here that's mapping out three different points. You can imagine that these are three places that an object or a car or a person walks through. And they're labeled A, B, C. And I've actually written down the positions of these three points in my coordinate system. Right? So that's where we're mapped out. And I've also specified the times at which I'm making these measurements. And you'll notice that they're not even. We'll start our clock at point A at 0 seconds. We'll reach point B at 1 second, and then we'll take another 4 more seconds, so at t equals 5 seconds, to reach point C. This will give us a chance to sort of look at how these different quantities differ if you have larger or smaller time steps. So we have to start with our definition of what the average displacement is. And this is actually average or instantaneous. It doesn't actually matter too much. We're just looking at the difference between two positions. And so if we want to look at the displacement between points A and B, we can write this down as just the difference between the position vector at point A minus position vector at, position vector point B minus the position vector at point A. And if we go back to our best practices for how do we add and subtract vectors, the best way to, one of the good ways of doing this is actually write this down coordinate by coordinate and do the math in that direction. And so if I write down these coordinates, so I'll start with B, and that's 2.0 and 3.0 meters, and I'm subtracting off A, which is 1.0 and 2.0 meters, all right? If I just divide up this subtraction into the different coordinates, I can just do this very simply. 2 minus 1 is 1.0, and 3 minus 2 is 1.0. And I've got my displacement vector just like that. All right? And so that's going a displacement of 1 meter in both directions. And we can double check this graphically by just drawing the displacement vector between these two positions. R, delta R, AB. And indeed, in order to draw that vector, I had to move over 1 point and move up 1 point. So that's consistent with the number that we did numerically. This is a great example of how you compare a numerical answer to a graphical double check. Now let's quickly just write down the displacement for the next step, which is between B and C. That is just the difference between the position vector at C minus position vector at B. Again, we'll write down the coordinates and do this by coordinate math. All right, if I separate these out, 3 minus 2 is 1, and 1 minus 3 is minus 2.0 meters. So that's my displacement vector from B to C. And again, I can double check this graphically by just drawing that vector, delta r. Very hard to write this way. Okay. And indeed, to draw that, I had to move over one spot and down two, and that's consistent with my displacement. All right, now, to go from displacement to the average velocity, we go back to the definition of what velocity actually is. All right, velocity, as we said, is equal to the displacement over time. And so if I want to look at the velocity between point A and B, for example, then that's just equal to the displacement vector that I just solved divided by the time step between A and B. All right? And now this is an example of multiplying a vector by a scalar, that scalar being 1 over the time step. And we know how to do this math as well. All right? The time step is just the time between A and B, which is 1 second, so I can divide by 1.0 seconds, and then multiply this by the vector coordinates that I've already solved, which is 1.0 meters. And this is probably the most difficult math problem we've done so far, but this is just equal to 1.0 meters per second. Okay. Now, notice that I was very careful about keeping my units as I was calculating here. I've kept my meters per second so that I could write down the right units at the end. And I was, even though this is a pretty easy problem, you're really dividing each of these coordinates by the number that's out in front here in order to get your final answer. Okay, pretty simple. Let's look at the relation between B and C, the velocity between B and Z. This is exactly the same expression. All right, delta RBC divided by the time step. In this case, our time step is going from 1 second to 5 seconds, so that's 1 over 4.0 seconds. And we've already calculated the displacement, that's right here, so 1.0 comma minus 2.0 meters. And we calculate that all out, we get 0.25 comma minus 0.50 meters per second. Okay, a couple more things. Again, we want to reflect on how we've done this calculation. We've kept the units carefully secure, so we have the right units at the end. Notice that I've also been careful about making sure to retain the right number of significant digits. It's actually not hard in this case because they end up to be the same number of significant digits as I start off with. But I start all these numbers have 2 significant digits, and so the solution at the end should also have 2 significant digits as well. Now, let's just take a look at these numbers just real quickly. I've written these in coordinate format, so we've got our sort of x and y coordinates for velocity. One thing to note is that they're pointed in exactly the same direction as our displacement vectors. And that should make sense because we calculated velocity as a displacement over a scalar. A scalar multiplication operation doesn't change the direction of our vector. So the velocity coordinate actually points in exactly the same direction as our displacement vector. The other thing to notice is that, in fact, this vector right here is a longer vector, a larger magnitude vector than this one. If I actually calculate out the components, the absolute value of VAB, or the magnitude of that vector, is just the sum of the square roots. So 1 squared plus 1 squared is 2 square root of that. That's going to give me 1.4 meters per second. That's a measure of the speed at which this object moved between A and B. If I did the same thing down here, right, same exact operation, what you'd find is that this is equal to 0.56 meters per second. And so even though the displacement vector is actually quite a bit bigger between B and C, because it's taking a longer time to get between those points, the velocity magnitude is actually smaller in that case. So let's start by first calculating our difference in velocities, and we're going to follow our best practices again for vector addition and subtraction. All right, we're going to write these down in their coordinates. So VBC is the number there at the bottom, 0.25 minus 0.50 meters per second. And I'm going to subtract off velocity between A and B, which is 1 and 1 meters per second. And this is pretty straightforward math. This is just minus 0.75, again splitting this along the coordinates, minus 0.75, and minus a half minus another one is minus 1.5 meters per second. Okay, now let's, so let's now calculate the time. We'll talk about the direction for this in just a moment. The time frame is the difference in the times, but these are kind of unusual times because we're not actually at points. We're talking about the times at which the average velocity was calculated. And so we kind of have to choose a couple of midway points here in the motion as our reference for the times. And so delta t is equal to TBC minus TAB. All right, we'll say these are the average times in between here. And in that case, between B and C, all right, the times are 1 second and 5 seconds. So kind of the average time is about 3.0 seconds. All right, and then the average time between point A and B is about half a second. Between 0 and 1.0 is about 0.5 seconds. And so the change in time is actually about 2.5 seconds. This is a bit of a subtle point, but it comes in having to deal with average quantities over sort of discrete time steps. When we look at the change of the change at some level, we have to look at the averages at which the points were actually calculated. In this case, the velocities were calculated. All right, well now we have all our numbers, so we can actually go ahead and calculate out our acceleration. All right, that's just 1 over 2.5 seconds times our difference in velocity vector, which is minus 0.75 and minus 1.5 meters per second. And when you do all the math, you get out minus 0.30 minus 0.60 meters per second squared. We gain another second by divided by the time here. Now, it's a good idea to kind of look at this solution again and see if it makes sense, at least graphically. This vector is pointing in a negative direction both in the x and y coordinates, and in fact if I just kind of sketch it out here, it's kind of pointing off in this direction. Right? It's got a little bit more negative direction in the y-axis than the x-axis. And so that's kind of generally what the acceleration looks like. And if we think about it, that makes sense because originally we had an object that was moving off in this direction and then changed its velocity into this direction. And so this change in velocity is actually pulling the object back down because it's going up and then it went down. And it's also kind of slowing it down as it went from this direction here because it took a longer amount of time to get from B to C. So at least qualitatively, the acceleration seems to be pointing in the right direction, and that at least indicates that we didn't get any of our minus signs wrong. So we've just seen an example where we take a few points positioned through space and use those to calculate the velocity and the acceleration, the average velocity acceleration. And that's very useful, but in most cases in physics, what we actually know is the acceleration because of the forces, and we're trying to predict what the velocities are or the positions are as a function of time based on those accelerations and some initial conditions. And so it's important to see how we go backwards through this process, going from acceleration to velocity to displacement as well. So if we start with the acceleration that we've computed, we can start to look and see how we'd actually piece back together these other quantities. So let's go back to our definition of acceleration, which is the change in velocity over time. And we can actually rewrite this because this is just a regular numerical equation. So we can multiply both sides by delta t, and we can get an expression for the change in velocity is delta A, oops, apologies. Let's erase that out. A times change in time, right? And delta V is just the difference in the velocities between two different positions. So if we go back and say, let's look at our difference in velocity between points B and point C, this is going to be the velocity, and I'm sorry, let's take a step back. If we look at the velocity difference between the motion from B to C versus that between A and B, this change in velocity is just VBC minus VBA, all right, our change in velocity. and that's just equal to our acceleration times the change in time between AB to BC. All right, so we've got our acceleration up here, so we could in principle calculate this because this is just the vector times scalar operation. So let's actually write that down, A delta t. All right, our components for acceleration are given up there, minus 0.30 minus 0.60 meters per second squared. And now we want to multiply by the difference in time, and if we recall, we had to kind of take averages between these two different time periods in order to calculate that. So we're really looking at the difference between 3 seconds and half a second, and so that time difference is 2.5 seconds, right? And we calculate that all out, and we should get back what our difference in velocity was last time, minus 0.75 and minus 1.5 meters per second. All right? And now we can go and actually compute what the velocity is at, for example, between the points B and C. That's equal to our velocity between A and B plus this change in time. Sorry, change due to the acceleration. Now notice something, we've been able to calculate this, but in order to calculate the velocity between the points B and C, we have to actually already know what the velocity is coming into that point, the velocity between A and B. So when we go from acceleration down to velocity, we actually have to have another piece of information in addition to the acceleration, and that's the initial condition, right? What is the velocity before you actually have this period of acceleration? So we kind of have to cheat a little bit, but we're not actually cheating. We would actually have to have these initial conditions to calculate this. So we could calculate BC as long as we know what this velocity was at A and B. So once we know that, once we have that initial condition, this becomes our regular vector algebra. All right, so we can just compute. We've got 1.0 meters per second for VAB, and we're adding our acceleration times time step. That's this quantity right here, minus 0.75 minus 1.5 meters per second. When we add those up, we get 0.25 on this side, and we get minus 0.50 in the y-coordinate side, and this is in units of meters per second. And this is equal to VBC. And if we go back and check, that's indeed what we calculated before for what that velocity is. So we've managed to get the right answer in this direction. Now, there's another way that we can check our answer this way, and that's again reverting back to the graphical representation of these vectors. I've eliminated my position map, and I'm going to replace it now with a map of the velocity components. So if we look at the velocity in the x direction, the velocity in the y direction, we'll give them some directions here, and I'm going to mark off ticks along these coordinates like we always do. All right, in this case, those ticks are going to be in steps of 0.25. So I'll just make sure to mark that off. And this is in meters per second. Meters per second. So we've got a perfectly valid coordinate system. In this case, we're just looking at it in terms of velocities, not positions. Well, why did I do this? Well, we can actually check to make sure that this math was done correctly. All right, we know that the velocity that we start off with, AB, is pointed in this direction. All right, 1 and 1, so this is velocity AB. All right. We should end up with a velocity that is pointed in 0.25 and minus 5. So that is this coordinate right here. This is VBC. All right. And in order to get to there, we had to add in this additional acceleration times time step. Well, that acceleration times time step is right here. That is going, on our scale, 3 units to the left, because these units are in 0.25 meters per second, and 6 units down. So 1, 2, 3, 1, 2, 3, 4, 5, 6. That vector indeed gives us our graphical vector algebra. VAB, right, tail to head, plus A delta t, tail to head, the resulting vector is exactly the velocity vector we're looking for. So again, this is a good way of double checking graphically whether the numerical calculation was correct. All right, now to close the loop, we've gone acceleration and velocity. Let's look at how we go from velocity to displacement and ultimately position. So again, we do exactly the same steps as before. We look at our definition for velocity is equal to displacement over time. All right, multiply both sides by delta t gives us an expression for the displacement in terms of the velocity times delta t. And the displacement is, of course, if we look at, let's take between A and B. So that's the displacement, or the position of B minus the position of A is equal to this average velocity delta t. You can see this looks exactly like the acceleration case. So we have to calculate our velocity times delta t. All right, this is just a vector times a scalar. We know our velocity, that's AB. Let's make sure we know which time step we're looking at. All right, velocity of AB, let's assume that that's something that we've just calculated in our previous problem. So 1.0 meters per second. And then we're multiplying by the time step. In this case, between point A and B is just equal to 1.0 seconds. And that gives us a simple calculation that the velocity times the time step is just equal to a displacement of 1 meter in each direction. And finally, if we want to then calculate the position at B, we have to know the original position at A, and then we can add in this velocity time step. All right? So assuming that we're given the position, our starting position at A, all right, that's equal to 1 and 2 meters on our coordinate system, and we're adding in our extra displacement from the motion. Again, doing our best practices of vector addition, we will get a coordinate of 2 and 3 meters for the position of B, and indeed that's what we ended up with before. All right? So again, we can look at this as a graphical sort of double check. It's actually pretty easy when we go back to our original coordinate system because we know that we started at 1 and 2, and we know that we should end up at 2 and 3 based on our graph, and that is indeed the numerical answer we got in the end. Of course, the other way to look at it is that this displacement that is caused by the velocity is just equal to this displacement vector here, and that's equal to the number that we came up before. So multiple ways of double checking your numbers, but in the end, as long as you've done your math carefully and coordinate by coordinate, you can go back in either direction between position to acceleration and back again. So to summarize, when you're looking at the transformation between these average kinematic quantities, you can follow these sort of equations which really come from the definitions of these quantities. That the displacement is just the difference between two positions, that the time span is really the different times where you're measuring these positions, and you can calculate the velocity as just that displacement over the difference in time. And because this is a vector divided by a scalar, the velocity is going to point in exactly the same direction as the displacement. All right, that scalar quantity won't make it negative, or sorry, won't make it in a different direction. If it's a negative time, it may be, but we're mostly talking about forward time, so this is going to be a positive quantity. You're going to have the velocity vector parallel to the displacement vector. The acceleration is looking at the difference in velocities between, say, two pairs of points, and so you really need at least 3 points to calculate this quantity. And so it's the change in velocity over an average difference in time, which is really the sort of difference between the times that are sort of in the middle of your two steps, and then the difference in velocity, of course, the velocity is calculated for each of those two different displacements. So it's a slightly more involved calculation, but as long as you go step by step, you can get all these numbers correctly. Now, as you're going from displacement down to acceleration, that's really just a matter of calculation, all right, measuring those differences in position, calculating those differences in time, and then working through the math. When you're going from acceleration down to displacement, which is the more common calculation you'll be doing here in physics, you have to calculate but also take into account the initial conditions. So you can't just go from an acceleration and figure out the entire path of an object. You have to know something about its initial position and its initial velocity. Now there's a couple tips that I want to make sure I leave you with from doing these calculations. First is to make sure when you're doing these vector calculations that you evaluate the coordinates separately. This is part of our best practices for evaluating vector subtraction and multiplication, which is sort of my third point there. The other point is to make sure that you check your answers. And one way you can check your answers is graphically. So you can actually plot those velocity vectors or those position vectors and see if they make sense. All right? When you add these things together, are they actually coming up to the right end result as you expected?